Welcome to the notes for section 11.1, an introduction to sequences and series. We need to first start off with some vocabulary words. Terms are not terms like you usually think of it. Terms are usually things that you add, and factors are things that you multiply. When we talk about sequences and series, terms are the numbers in the sequence. They're not necessarily being added, they're just the elements or the members of the sequence. A sequence is a function whose domain is a set of consecutive integers. If the domain isn't specified, then you just assume that the domain starts with 1. A finite sequence is a sequence where the number of terms can be counted and the sequence has a last term. An example of this would be 2, 4, 6, 8, 10, 12. Because there's 1, 2, 3, 4, 5, 6 terms, I can count the terms, so it's a finite sequence. An infinite sequence is a sequence where the number of terms cannot be counted. There's no last term and the sequence continues without ever stopping, such as 4, 8, 12, 16, 20. You can see the pattern. I keep adding 4 to get to the next term, but the terms never end. The dot, dot, dot at the end means they continue on forever. So an example that I'd like to go over is this. We want to write the first 5 terms of the sequence. A sub n is equal to 3n plus 5 is the formula on how to get each of the terms. A sub 1 is 3 times 1 plus 5, which is 8. A sub 2 is 3 times 2 plus 5 is equal to 11. A sub 3 is 3 times 3 plus 5, which is 14. A sub 4 would be 3 times 4 plus 5, 17. And finally, A sub 5 is equal to 3 times 5 plus 5, which is 20. You might notice that our sequence goes up by 3. 8 plus 3 is 11, plus 3 is 14, plus 3 is 17, plus 3 is 20. It's no coincidence that there's 3 right here in the formula. Our next example is to write the first 4 terms of the sequence a sub n is equal to 3 to the nth power. I can think of this as the domain, and remember that when we're talking about a sequence, the domain is a set of integers, consecutive integers. We're going to start with 1. So I'm going to have the domain be 1, 2, 3, and 4. My range would be 3 to the first, which is 3, 3 to the second, which is 9, 3 to the third, which is 27, and 3 to the fourth, which is 51. So the first 4 terms of the sequence are 3, 9, 27, and 51. My next example is to write the first 4 terms of the sequence -1 times 2 raised to the n minus 1. Notice that the n minus 1 is just next to the 2, it's not next to the -1. So when I substitute in 1, 2, 3, and 4 for n, I get the numbers -1, -2, -4, and -8. If f of n would have equaled -1 times 2 raised to the n minus 1. See, this is different because the n minus 1 is now touching next to the parenthesis, which includes -1 times 2. Then my sequence would have been 1, -2, 4, -8. The terms would have alternated between positive and negative. Example number 4. Write the next term and write a rule for the nth term. 1/2, -1/4, 1/8, -1/16. Each time I go from one term to the next, I'm multiplying by -2. So that would mean that my next term would be 1/32. The rule, to get the rule, I'm going to have to find f of n, which is equal to -1 raised to the n minus 1 times 1/2 raised to the nth. I need the -1 raised to the n minus 1 because these terms are alternating between positive and negative. Example number 5. We're going to write the next three terms of the sequence 3, 8, 15, 24, 35. If you notice, to go from 3 to 8, I'm adding 5. To go from 8 to 15, I'm adding 7. From 15 to 24, I'm adding 9. From 24 to 35, I'm adding 11. Now what we really need to notice is that what I'm adding has a pattern. 5 plus 2 is 7, plus 2 is 9, plus 2 is 11. So when I get my next term, I'm going to add 13, which will give me 48. Then if I add 15 to that, that would give me 63. And if I add 17 to 63, I get 80. So my next three terms in the sequence are 48, 63, and 80. We need to know a little bit more vocabulary in order to go on. We talked about a sequence. A sequence was a list of terms. A series is when you take those terms and you add them together, so it's a sum. A series is the terms of the sequence that are added. There's finite and there's also infinite series. An example of a finite series would be 1 plus 2 plus 3 plus 4 plus 5, because I'm adding 5 terms. I can count to 5. That's finite. An infinite series would be something like 1 plus 2 plus 3 plus 4 plus 5, but then you have plus, and that dot 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 means that you go on forever. Now we also need to learn a new notation in this section. We're going to be talking about summation notation. This is a notation for a series that uses the uppercase Greek letter, which is called sigma. For example, you can write 3 plus 6 plus 9 plus 12 plus 15, or we can do a shortcut here, and we can use sigma. Sigma represents the sum of the first 5 terms. I equals 1, that means I'm starting by putting in 1 into my formula, and then I would put in 2, 3, 4, and finally end on 5. I is called the index of the summation. 1, this number right here, which is not always 1 by the way, in this case it is. 1 is the lower limit of the summation, and 5 is the upper limit of the summation. Now I can write a series with summation notation. What I need to notice here is that I'm going up by 5. Again, I'm going up by 5. I'm going to continue to go up by 5 until I get to 100. Now, 5 represents my first term, 10 is my second term, 15 is my third term, and I'm adding all of these, and I'm going to continue to add until I finally get to 100, which would be my 20th term. So when I write this in summation notation, I'm going to use sigma. I'm going to have I equals 1 to begin with. That doesn't mean my first term is 1. It means I'm putting in 1 into my formula. I'm ending on my 20th term, and the formula for this is 5i. If I put in 1, I get 5. If I put in 2, I get 10. If I put in 3, I get 15. I'll explain more formulas for for ways to get this later. Right now I know it's a bit frustrating when we're just going from one term to the next and I can give you the formula, but I promise that'll get easier in just a little bit. Example number 7. I'm going to find the sum of the series, and notice that I'm given summation notation. So I'm going from the first term, I'm going to put in 1, then I'm going to put in 2, 3, 4, and finally end on 5. So when I put in 1, I have 3 times 1 plus 3 times 2 plus 3 times 3 plus 3 times 4 plus 3 times 5. And I want to stop there because that's my upper limit. Now I just want to simplify. I have 3 plus 6 plus 9 plus 12 plus 15. And when I add these together, I get a grand total of 45. So the sum of the series is 45. Example number 8 is very similar to the last example that we did. However, the index is starting with 2. So that means first I put in 2, then I put in 3, 4, and stop at 5. So this is equal to 3 plus 2 times 2 plus 3 plus 2 times 3 plus 3 plus 2 times 4 plus 3 plus 2 times 5. And now I want to simplify this. This is 3 times 4 is 7 plus 3 times 6, 3 plus 6 is 9, 3 plus 8 is 11, and 3 plus 10 is 13. And when I add all of these, I get 40. Now the last couple examples that I did, I found the sum, and in number 8 I went from the second term to the fifth term. So really I only had to add 1, 2, 3, 4 terms together. In the example before that, I went from 1 for my lower to 5 for my upper, which meant that I had to add 1, 2, 3, 4, 5 terms together. Now that's not so bad, adding 5 terms. But if the number above here would get really high, if I had to add these together each time, that would get really long. So fortunately for us, we have some formulas to help. The first one is the sum from 1 to n of 1, which is n. The second, going from the first term to the nth term, so I'm going to be putting in 1, 2, 3, 4, 5, and so on. So this basically means 1 plus 1 plus 1 plus 1, and I have n terms. This one means I put in 1, and then 2, and then 3, until finally I get to the nth term. The last one, the last formula, I'm going from 1 to n, and I'm putting that into I squared. So that's like taking 1 squared plus 2 squared plus 3 squared plus, and continue that pattern until I get to whatever the nth term is. So using these formulas will be a lot easier if n is really high. So let's use one. This time I'm getting I squared, and I'm going from the first to the fourth term. So using the formula, that would have put in 4 for n, and then 4 plus 1 is my n plus 1, and then 2n plus 1 is 2 times 4 plus 1, and that's all divided by 6. When we calculate this, we get 30. If I'm trying to simplify the sum from the first to the sixth term of I, that means I'm going to use n, which is 6, times n plus 1 is 7, all over 2, which gives me 42